Here's another AP problem to give us further practice in our study of work, energy, and power. This one happens to be from the level B AP exam from the year 1997. Now, I'm not going to answer every part of it, but I'll at least give you hints to each part, and a couple of them we'll do in full. So we're told that a 200-gram object, or 0.2 kilogram, moves along a straight line path. The net force is shown by this graph. The object starts from rest when it's at the origin, which is our initial moment in time, and ultimately it travels a full distance of 20 meters. So we have to determine all the following quantities, A through F. So the first one, find the acceleration when the displacement is 6 meters. So let's just find where 6 meters is on our graph. Okay, read up here, got it. So I guess the value for force is 4 newtons. All I'm going to say here is acceleration can be found by dividing force by mass. I'll leave that up to you. Part B, find the time taken for the object to displace the first 12 meters. So we notice, because the force remains a constant 4 newtons all the way up to 12 meters, constant force means constant acceleration. And when acceleration is constant, you can use kinematics. So if we're told there's a distance of 12 meters, and we've already found an acceleration in the previous part, then I'm going to say I leave it up to you to find the right kinematics equation to solve for part B. For part C, find the amount of work done to displace the object for the first 12 meters. Okay, well, work can be calculated a few ways. It's the vector dot product of force with displacement, or it's the scalar product of the force and the displacement times the cosine of the angle between the two vectors. If force isn't constant, then the work is equal to the integral of F ds cosine theta. But more importantly, to this problem, work can be calculated by taking an area. We just need to find the area under the curve up to 12 meters, which couldn't be easier. This is just the area of a rectangle with a width of 4 and a length of 12. So very easy mental math here. 48 joules of work are done for the first 12 meters. We're going to use that to get our answer to part D. Now we're asked to find the speed of the object when it reaches a position of 12 meters. So for part D, we're going to employ the work kinetic energy theorem. Work is equal to an object's change in kinetic energy. Because we were told that the object starts from rest, change in energy is final kinetic energy minus initial, but the initial was 0. So we really have the work is just equal to the final kinetic energy of the object, but final kinetic energy is 1/2 mv squared. So when we rearrange this equation to solve for v, it's equal to the square root of 2 times the work done divided by the mass. And we know how much work is done, 48 joules. So 2 times 48 divided by, let's see, do we know the mass? Sure, that was given as 0.2 kilograms. So this is the square root of 480. And we get an answer of 21.9 meters per second. Part E. Now we have to find the final speed when the object reaches 20 meters. I'm not going to solve for this one, but I'll give you a hint. We know it takes 48 joules up until 12 meters. So let's find out how many more joules of work are done to go from 12 meters to 20 meters. Well, again, that's just calculating the area under this part of the curve. So if we can find that area and add it to the 48 joules we already found, then that would be the total work done from 0 to 20 meters. So we're going to end up just using the same formula once again, but just changing the value. This will no longer be 48 joules, it'll be some value you can easily determine. And so the answer is not going to be 21.9 meters per second. It'll be some greater value, but I'll leave that up to you to figure out. Lastly, part F, we're not going to investigate that at all because that's a subject for a future unit of study. We won't investigate momentum for a couple more chapters down the line. Okay, thanks for watching.